Okay, so here we're gonna formally define what a span is. All right, so we say that a span of a set of vectors. So here, let's formally define this. So given a set of vectors, we'll call S to be U1, U2, all the way up to UP. All right. So we have a set of vectors, all right, coming from our vector space. Right now, we're just talking about Euclidean space, but we're not really uh, held to it being from Euclidean space. It's really very generally a set of vectors. Right? Their span which will use the notation to be this. All right, these types of brackets here. All right. So when we see that notation, we know that it's referring to the span, right? As we saw in some of our worksheets in class, right, it just had spelled out span, and used curly braces, right? So either or here, we'll just use the convention that is used in our textbook, where we use this type of notation. So the span of S is the set of all possible linear combinations. Okay, so written out mathematically, we say span of S is equal to alpha 1 U1 plus alpha 2 U2 alpha P UP, such that alpha sub I is an element of real numbers Okay. Okay. All right. Sorry, the pen is a little slow today. I have no idea why. So, okay. So that is the span, and then a compact notation would be using our sigma notation. Okay. So that's the notation that we use for the span, right? Now, as we saw in the previous video, right, when we had these two vectors or just vectors in R2, right? So the options were really the vectors they could span a line, right? That was the structure that it built, or if it was the correctly chosen vector, we could span the whole space. Right now in R3, we went up a dimension and we could see where there was more options, right? We still had that line option, but we also had a plane, right? And then with the choice of the vectors in the proper way, we could also generate the whole R3 space itself. Okay? And then again, we'll tie all this with our linear dependence and this idea eventually of dimension of a vector space, right? So we could see the types of structures that can be built within the larger vector space, right? So some examples here just of a linear combination, right? So let's say we had a set consisting of V1, V2, and V3. All right, and these vectors are defined in the following manner. Negative 2, 3, 1, 0, 2, 3, and negative 3, 4, 1. So we'll call this set S. All right. Okay. And now a linear combination. Now, one thing to keep in mind here, the set S is a finite set, right? The set S consists of three elements, V1, V2, V3, right? The span of S is an infinite set because our scalars here become all the different linear combinations, right? So for all choices of real numbers, right? So again, my set S is three elements, right? So when we look at, well, what is the size of this set, right? S contains three elements. Right? The span of S contains infinite number of elements. All right. So just keep that in mind, right? As we kind of refer to these sets, we can understand what the difference is in these two because they are very, very different, right? Okay, so examples of linear combinations, right? So here, just some examples as right. So here we could have one example again. It's just like 1, negative 2, 3, 1, plus negative 2, times 0, 2, 3, and let's say plus negative 1, negative 3, 4, 1. Okay, so we have this, and then using our vector operations, right, we have here, I can add these to be negative 2 plus 0 plus 3, and then here 3 minus 4 minus 4, 1 minus 6 minus 1. All right, and then here combining these, adding them up, we have, what is that, a 1, negative 8, negative 5, negative 6. Okay, and notice this is an element of the span, right? Just by definition, right? It's a linear combination. All right, but again, if you look here, it is not an element of the set S. All right, so here I keep bringing this up because I do just want us to understand there's a distinction between both of these sets, right? Any set, any vector that can be written as a combination, linear combination of vectors in the set S is in the span, right? But not necessarily in the set S, right? The set S is very finite. It consists of these vectors, v1, v2, v3, right? Although, right, just kind of continuing on this, v1 is an element of the span. So is v2, so is v3, right? Because we can think of those as linear combinations where I can set the other two scalars equal to 0 and set the one that is non-zero to 1, and then you've retrieved the vectors v1, v2, v3. Right, so that's also good to understand here, right, that for our example above, v1 is an element of the span of S. Right, and so is v2, v3. All right, and it's also an element of S. Okay, all right. So that's the idea of a span, right? So next, the kind of question we want to ask is, well, how do I know when a vector, if I have a vector, and if I have a vector S, how do I know if that given vector is in the span of S?